Good evening, everyone. Welcome. Need a new browser window, damn it. Not the incognito one, though. Trying one of those ones. So, I will get to explaining, I'm super quiet. Oh, that's weird. I don't know that I should be. I mean, I'm looking like I'm at normal levels. I might have to go and poke, holes. Sound... possible dual volume control. Did it go messing with my input? Well, a little tiny bit. No, it looks like it should be fine. Anyway. Yeah, ping me if the audio gets any worse or I need to go and mess with volume controls. So, tonight I'm planning to take the firmware for Blackmagic, which, if I'll poke this repo, we've already cloned. Because we're going to do some changes that are not yet going to go public. Well, I'm going into the yellow Aki, so I can't really do much to my volume levels, I don't think. So the plan today is... Okay, interesting. I might have to poke that some more then. The plan today, though, is to try and build a new target for Blackmagic Probe, and possibly look into trying to build a image from an ELF file, because the project that I've become involved in needs onboard flash, be able to temporarily store a bitstream or a piece of firmware that then gets put out with the click of a button to a target. It's a known in advance target, but we need to do some pre-assembly of this image that will sit in the flash so that Blackmagic can read it back in and reparse it to do the right thing to the target. And at the same time, obviously Blackmagic Probe needs some way to be able to write that flash in the first place from GDB with our binary file that's been pre-assembled. So, today is all about trying to do that first part. We're looking at the attach, erase, write, and possibly also like mass erase parts of the target API. So, it all starts with a new target. I'm actually going to throw the STM32 stuff over here as like a reference, because it is quite well written. And yes, this is also the same code that we'll be needing to poke into from the target API when the button's pressed, because of the specific target that we're going to be doing this firmware for initially. So, that adds the new target. Some godforsaken reason those are all tabs. Fine. Make file tools there is being a bit confused, but that's make file tools for you. Oops. So this will be there we go. Took it a moment for it to kick in, but there's the automatic star stuff doing its thing. This will be copyright 2021 Rachel Mant. And it looks like this is GPL, so let's do SPDX license. Oh, I'm trying to remember how this works again. Oh, did I? Okay. SPDX license identifier. There we go. So this is GPL v3+. Well, actually, it's all later because of the way that SPDX works. So we I'm trying to work out how this target is created. That's going to be part 1. How's everyone doing though, by the way? Or pets. Aki needs pets. So Cortex here, is based on the ADI v5 APT. Which I think is going to basically be go look at how ADI v5 SWDP scan works. To understand, which that's not where it's declared you. Dumbass IDE. There we go. Okay, I'm going to start with figuring out how to implement the new scan type. That'll probably be the easiest place to do this entry, because then we'll know exactly how the target chain is created. So this will be onboard flash scan. And we're not going to do anything with T, because target can be null or the previous target or what have you, and we don't really care about that. We don't need to deal with target voltage because this is on the board. Oh, I also should bring up the schematic, I guess, so I know what the pinouts are and what SPI controller I've got to use. So we have, yeah, there's the SPI bus there on SPI 2. So it's just going to be target list free. Clean up the target list. Jeez. This is some very weird pattern going on there. This is to do a stack allocation. How is the JTAG one done then? This is done using JTAG scan, which is... implemented in JTAG scan.c. Wonderful. Oops. So, header for those is target H. I don't actually know that I need that parameter. Because there's no such thing as a target ID for us. There's only going to be the one flash chip on the board. So this is int device count is onboard flash scan. But I have no intention of actually triggering any exceptions at any time. I guess what we can then do is if devs less than or equal to 0, gosh, I hate this style, but hey. GDB out, hey Steffi, welcome, welcome. Welcome, Direct Boom. And it looks like I then want to do CMD targets with the null target, no args, and make sure that The LEDs are off. Oops. True, true. Good job, me. Try return. We then get to add that as a new command. This is onboard scan SMD handler CMD ooh, fun. Also, if I'd remember to put CMD on the front of that, I guess. Scan. For on-board SPI Flash devices. Yeah, that should do the trick for creating ourselves a command that we can use to actually initiate this chain. So the actual scanning itself... Gosh, some of this is very spaghetti code. That's... How is JTAG scan working? Is it less painful? Tapping it. We have to do the scan. Getting out instruction registers. Ah. So where's dev description? Okay, yeah, that's about as spaghetti as the other one. JTAG devices. Just appears. Cool. Oh no, JTAG devices is read there. This is JTAG device S. In both cases, I'm not sure how we end up in the target code, which is bad because I kind of need to know. The Cortex-A probe we get to from this. Which is part of ADIV5 DP init. Is this the bit that actually finally gets called from that's in target? What? Why is that in target? Well, there's the target list getting cleaned up. Oh, line 60. Going down when it should be going upwards. No, I just can't read what file that's in. Whoopsie. These are both targets. So this is the one for... Oh, okay. Gosh, this is trickier than I was expecting already. So when doing the scan, it does some fun stuff to do with setting up the scan chain. And then once it knows how many things are on the chain, it goes through and eventually, once it's figured out the ID code and some other bits, does this ADIV5 DP init on the ADIV5 DPT, which is this horrific thing. Kind of already hate that. So if we look at how this works, it figures out some information on like what the device is and how to treat it. Including like device-specific probes. I think that was then calling into this. No, that wasn't the one I want. Confused. Very confused. Ah, it ends up calling into component probe. That calls itself. Cool. Oh, after the ones for like Kinetis, etc. So once it's gone through all of these different things, trying to figure out what this is, a fallback is it just does a component probe. And that figures out whether it's a Cortex A or not. And if it's a Cortex A, we then get to... Yeah, okay. So we can skip all of that pain. Because we know that there's a single thing on the chain. So target T is target new. If not T, then we get a return -1, or we didn't manage to do a scan. Then, gosh, this is so spaghetti, it's ridiculous. Target list, question mark, 1:0. Okay. I'm guessing target list is supposed to be defined by target H. I can't tell. Let's do a search for that. Oh, target internal. That's where that's coming from. So, with a target, okay, we get the ability to have some private context, but we don't necessarily need that. We then have... most of these get defaulted, so we actually only need onboard flash attach as a thing. Then onboard flash erase struct target flash f target address and size t length. Apparently I've just gone over the indentation limits, etc. That's not consistent. Wonderful. So this is flash, no. Really? Oh, this must be a thing specific to... the target flash. That's right. Yes. So we have to do target add flash because we'll need to be able to pull out how much flash we have available on the bus. Okay. So this is the flash chip that we'll be using, which, yes, it's a nice big flash chip. It's what we could get a hold of that fits. And if we look down through, there should be an instruction around here for pulling out vendor data, essentially. I think, is it 9F? Looks like 9F is going straight past it. JEDEC ID, there we go. Yes, so if we do a 9F, now we do the appropriate target flash add to the target, some flash. Let's see. Well, let's do onboard flash add as the thing, giving it a target, and it can figure out everything else it needs from there. So struct target flash f. We probably want to do the thing that this is doing, creating a structure for this. So this is onboard flash struct target flash f, and then whatever we want to do follows after that. Try OF. Calico. Apparently I want to make this into a cat. Fun. So, F is the address of that. We'll figure out start and stuff. If I now do O. Huh. That's really curious. I'd expect that to read it as like all zeros or all Fs or something like that. But I guess it's injecting a... Oh, right, yeah, because it's probably injecting onto the chain the write it's doing to do the read, because you have to write to read on SPI. It's probably injecting that so it can detect for shorts. So the start of this flash block is going to be at 0. We've got to obviously figure out the length based on poking the flash and all of that fun. Oh, that works. I wish they'd document that kind of thing, though. So onboard flash write needs to be struct target flash f target address, destination, const void star, source, size t, len. And we'll also figure out, like, the sector sizes, etc. when we've got the data back from the chip. So, let us start writing some SPI Flash routines. Now, let's also check what the STM32 SPI support here has available already. Because this is using OpenCM3. So, okay. Init master. Would help if I knew what those two did, but you know. So this is for the F1 that we're targeting. I might need a datasheet from the manufacturer real quick. Manufacturer's datasheet, in fact. Oh, hi, Sylvia. Welcome. Just pulling a datasheet because, well, you know how this goes. Welcome, welcome. So far, I'm working on trying to start extending out the firmware for Blackmagic Probe so that it has support for an onboard flash chip, among other improvements that are being made in a project that I'm involved in. And I have just started writing, well, I've just been working on writing the scanner for the flash chain because, you know, SPI bus and the way that the target system works. Building a target, building a piece of flash attached on that target, etc. And we're currently looking at how to do SPI on the processor that's used on native, as I'm using SPI bus 2 on that for the flash chip, and we need to go and poke it and pull out some information from it to know that it's the right flash chip and how big it is and some other bits. So I'm currently going and fishing in the datasheet for how the SPI bus stuff on this thing works. I have the funny feeling this is not the full datasheet. This is not the full datasheet. Yeah, it's the reference manual. And it's the 6. ST. This file, which is a lot longer. Thanks, Eston. So, where is SPI bus? Come on, SPI bus. RTC, watchdog timers, flash, SDIO, USB, CAN, SPI. Hey, there it is. Because unfortunately, a OpenSM3 doesn't actually document what 2 of the bits I need to know about do. So, the information that I'm looking for right now, it's... what DFF 8 and 16-bit do and mean. I think I probably want to do set DFF 8-bit because I'm doing 8-bit transfers. Oh, welcome Raichu Knight. But I need to confirm for sure that that's the right thing. Okay. Where are the examples in the codebase? I'm guessing here? No, that's DoxyGen stuff. Oh. Oh. Okay. Mind giving me a link? So I actually don't know where I'm looking for those. I've only ever used this in relation to projects that already have it integrated. Oh, thank you. So we are on STM32F1, and we are interested in... Okay. Oh, I see. So we'll have done the SPI setup elsewhere in this code. Now, okay, SPI reset. SPI bus 2. We want to initialize it. I don't want very much clock division on the baud rate. CPOL is going to be clock to 0 when idle, I think. We can change that easily enough. CPHA is mode 1, let's call it for right now. Data frame format, okay. 8-bit is correct. I'll check that that's MSB first when we look in the timing diagrams below. Setting NSS high is very important. Even if we're controlling the GPIO ourselves, this bit needs to be at least set to 1, otherwise the SPI peripheral will not send any data out. Okay. I'm guessing that applies here. Sure. In this case, though, I think it's going to be better to pull just the bits I need out, because I'm going to need to write routines for, like, blasting data to the bus, etc., and wrapping stuff up. Otherwise, I'm going to end up with duplication all over the place. So this is going to be where I initialize the bus, and then a couple of routines for reading and writing, because we're also doing manual control of the chip select, etc., and you know how this goes. Apparently I need to do that, otherwise this is going to break horribly. And then enable the peripheral. Let's have two functions, SPI write. I'm not yet sure what it needs to return. This needs to take a byte. And it will also be static so that it's TU local. Excellent, and it's SPI write. Onboard Flash. Well, onboard SPI write, that'll be fine. So I can then use SPI write, SPI to value. Ooh. Actually, it's SPI exfer, because we might actually need to know what's being done on, like, what bytes are coming back. I've also just realized I'm actually going to want these inline, because otherwise they won't get optimized out, which would be bad. Excellent. Oh, and yeah, read doesn't take a value. Onboard SPI select. I look forward to it. Yeah, indeed. So this is probably going to end up having to be GPIO set val. Yeah, probably set val. The port and pin is B and 5. We want constable value If that, then... Oh, okay. I can just pass a value in there. I don't need to do anything special. Excellent. So we do select. Oops. That tilde. Onboard SPI right. Now this is going to be... Ugh. Fair enough. I need to grab another window real quick. That one. Where did I put all the constants for... it must be in USB protocol then. Yeah, where's the SPI opcodes? So this is another of my projects, which I was aiming here to just go and grab the constants I already wrote. Oh, there they are. They're just right in front of my face and I'm completely blind. As this already has like all of the how to figure out what a chip is and so on, opcodes. I should just do this the smart way. There we go. DC++ them. Like that, and then we can just do JEDEC ID. And then the JEDEC ID gives us the manufacturer and ID numbers. So we'll do an onboard SPI read for the manufacturer, and then Unit 80 ID 2, ID part 0 is onboard SPI read, and ID 1 is then onboard SPI read, onboard SPI select false, which frees the chip back up. Now, how does that decode? Because I know SPI Flash programmer knows how to figure out how much flash is present based on that information alone. So there's a local capacity. I think this is in spy.cxx. Yeah, manufacturer type capacity, that's what's supposed to come back as the ID components. And if we look, manufacturer, should be EH, and then ID does different things depending on which instruction you use. This is horrible. Why did Winbond do that? ID 0 should be the first part, should be that 1.8, which is the type. Local capacity should be the other part. So 70, which is 2 to the 70, I think it is. I was gonna say, I'm not gonna go diving into it unless you just give me a link, because I don't know, okay. Thank you, I'll have a look in a moment then. So power of 2, the capacity number, and that should give me the right number. Probably. So F, size, no, not buff size, not block size even. Length is power 2 ID 1, which actually let's do this properly. Constant uint8t type, constant uint8t capacity. IceProg would already break in this instance because it's going to read the manufacturer ID twice rather than what it actually is expecting, because this chip only gives out 3 bytes, not 4, for JEDEC ID. That's fun. I guess this is dependent on the device to some extent. Anyway, yeah, that should be the capacity. What I was just going to check was that that is actually correct by taking x70 and putting that through Rink. 2 to the power of 70x in millibytes. This is there we go. No, that was right the first time. 4.9. Huh. That seems off, actually. This should have, $256 for 64 kilobyte blocks, so that would be 256 by 64 KIB. Actually, I don't need brackets. in mebibytes. We're looking for 16 mebibyte, which makes sense because this is an 128 megabit part, if I've recalled the numbers right. So WinBond is doing something weird here. We can also do some quick checking. If not, oh wait, sorry, if manufacturer not equals EF, debug on expecting WinBond serial flash device. SPI Flash device. Manufacturer ID is %O2X. So what are we missing? We've now got start the length, although that's wrong and we know it is, but we'll come back to that. Block size, so the block size for erase is 64K, but, well, can be, it can also be 4K. The block size for write is 4K, I think. Read data, 03. Let's go and have a look at 03. Oh, at least 1 byte of data is, input is required for page program. Up to 256 bytes of data input. If more, we wrap. So a page is still 256 bytes. Apparently. Well, that's to do with the security stuff, it looks like. Yeah, okay, 256 byte page buffer. So a page size... which is going to be the block size, is 256. My wrist is deciding to be a pain. Got the whole write enable thing to do, that's fine. Read data. Read instruction allows one or more bytes to be read sequentially. This is only supported in standard SPI mode. So it's byte addressable, that's what the 24-bit address is for. We're not doing fast read because we're not in a multi-bit SPI mode. And 256 bytes is again mentioned as being the page size. Cool. Okay. So we've got a block size. Buffer size and erased. F when it's erased is going to be hex FF. I'm going to set the buffer size again, same as on the STM32 to 256 bytes, which is 4 pages. Not yet sure what those other two do. Well, actually, those are specific to the STM32 stuff, so that's fun. And then we do the add flash. Yeah, they really do not want you to know how to decode their manufacturer ID, etc. Well, so the IDs actually have got a standard per JEDEC. They are supposed to put the capacity out as the second. Oh, sure, if you want to know, like, block sizes, etc., but if you want to know the raw capacity, you actually have to be able to read that from the ID code that they give you. So it looks like it's actually 1.8 is the value. So if I do hex 1.8, which was what they say is... There we go. Hex 1.8 in bytes, 2 to the power of that, and that is the number of megabytes available in the flash device. So this is actually correct. I was just not sure which way around these bytes were because their table above documents it wrong. Which is, of course, fun. Nice. So, are there any more commands that I need to implement here? Is there a read? No, there isn't a read. Oh. Well, thank you for the follow, Schmilin. Schmililin. Wow. Thanks for thanks for the follow and welcome to the stream. I'm sorry I've butchered your username. Let's see. So we've got flash setup. The next bit is to do reading and erasing. Sorry, writing and erasing. We'll come back around to attach, because attach is just really dumb in this instance. So we've got onboard flash erase, struct target flash f target address and a length. Also, I'm going to put some constants in here because I do not intend to touch certain things. Why would I? Oh, will that work? Yeah, that should work. That should work. So get out the target. Target storage. I'm not sure I actually need this, so I'll just put a comment on it for right now. Because what we want to do is this is doing while len. For size t, I is 0, I2 len I plus equals now it's not the sector size because this is kind of stupid. We actually want to... It'll be probably page erasure. No, not page erasure. That's the problem. That's... we can't do page erasure. It's... block erasure. Sector erasure, sorry. There we go. Sector, the 4K bytes. So this is sector size. That presents a second problem, actually. So this is that. Now, I can't put the constants in, darn it. This code base is not const clean, which is annoying. We're going to want a member here for the sector size, which... we can initialize here. This is 4096, 4K. And then down here we'll be able to pull out that sector size information and use it. Instead of having to say struct everywhere, I'm also going to make this a type def. So we've got onboard flash, OF is onboard flash pointer to the target flash. Now, if I'm not mistaken, the way this should work is I have to capture the SPI device, do a write unlock, which is write enable here. And then onboard SPI select false. Yep, that's right. And then we do a chip erase. Well, in my case, in SPI Flash program, I'm doing full chip erase, but in this case, we want to do sector erase and wait for it to finish. So SPI select, right, and then deselect again. And sector erase takes a 24-bit address. Which unclear. I think this doesn't have to be aligned to the start of the page, it just has to be somewhere in the page you want erased. So we've got target address, what is that? That is a uint32t, excellent. So we've got sector address is the address plus I, and then it's sent most significant byte to least. No, sorry, least significant byte to most, big endian style. So this is shift to the left by 16. And that takes a uint8, so that's fine already. Onboard SPI right sector address 8, and then sector address. And then wait for the completion of the erase. And this is the busy bit being set to 1. If we look at busy, somewhere around here is the how to read out the status register, status read. And if I can find it, that will tell us exactly how this works. Busy is bit 0, so &1. And status read is indeed 5. Yep. Or as I also sometimes call it, the la 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 not listening bit. Welcome Platypus with cheese. So it looks like if I were to hold status, chip select low, I can continually read all the status registers out, but I would have to go through 2 dummy cycles every time. Oh no, never mind. It's just continuous read of the same register. So, onboard SPI select true, onboard SPI write, status read, while onboard SPI read, and 1, continue. Onboard SPI select false. And that's already got erasure done. Need to know what to return from this function. Looks like it's just return 0. Perfect. And then we've also got to do writing. Writing is not dissimilar. Const void source size t length. This is the one where we get to use the block length we defined. So for size t, I is 0, I is less than the length of the buffer, I plus equals block size. So this is page address is the destination plus I. Onboard SPI select true. This is again, I'll just copy this. This is again enabling the use of the destructive instructions. Set up the right of the next page required. Onboard SPI select true onboard SPI right. This was page right. Onboard SPI right. Now we have to give it the address that we want to write to. Yeah, I'm just going to work on this based directly on that address. And then finally write out the data for the new data for the page. It's a good, you know, happy one. So this is for each byte in page. Ooh, right, because this is page size based. So this is the length minus I less than f block size then that else block size. I'll also mark a few of these things const because we are not going to change them. And then we can do onboard SPI write source I plus j actually this will be buffer because we actually need to do a recast, so this is const char star const buffer is src. So we've written all the data to the chip. We do onboard SPI select false, and then wait for the completion of the write. And that's how you write SPI Flash. That's really how simple that is. We could do a mass erase command. Yeah, I'm going to do a mass erase command. That makes sense to me to be able to invoke to bring the flash chip into a known state. I'm actually just going to call it mass erase. And this is a per target command. Which is why it takes parameters. So we've got void argc to shut usage up, void argv to shut usage up. We don't need that. We actually don't need the for loop either. The way that mass erase works is basically you tell it, I want to do a mass erase, and it goes away and thunks, and then eventually gets back to you and goes, there we go, done. This also returns bool. This is bulk. Oh. Bulk arrays? Chip arrays. In this case, I don't really need to... Fair enough. In this case, I don't really need to worry about the geometry exactly, as long as I'm doing a reasonable erasure size, which I think this is granular in... It's as granular as we're allowed, so... Oh, it will make it slow, yes. But also, if you're really that worried, you can just do a mass erase. And then everything else will be really fast because it's already erased. And the chip knows that, because it can check that very quickly. That's true. Hey Amy, welcome, welcome. So this is chip erase. Yeah, we got the right constant. It's nice how those are consistent between chips. Yeah, let's just send the instruction, no need for an address. Perfect. Set up the chip arrays, wait for the completion. Yeah. This is the addition of an extra command, of course, so I need to define it up here. Oops, there we go. And then I think, is it target command add or something like that? So you've got... target add commands, there we go. And apparently the target memory map, etc. is all done at attach time, so I've got to move a little bit of code around. Because add flash here shouldn't be fired here. So probe. That's a good thing we needed to implement that next. So attach should target free. Oh, sorry, mem map free target. That deals with adding RAM. And we add flash. That. Return true. And the probe part is setting up attach and driver, and sometimes detach. So we set up attach. Driver is onboard SPI Flash, because I'm just going to hardcode a constant. Okay. And then we can do target add commands to the target onboard CMD onboard flash CMD list driver and we then get to use this thing. There we go. Oh, right, and it's also not target flash, it's just target because this is one of those commands. Yes, this is C. This is the firmware for something that I'm adapting. This is the firmware, in fact, for Blackmagic Probe, the debugger you've seen me use before on streams. So, onboard mass arrays, const struct command. I bet this can be done without needing the struct if I do that. Arrays, well, mass arrays, CMD handler, onboard flash mass arrays, arrays, entire flash chip. And a sentinel value, because that's required. Flash internal, oh sorry, target internal. Oh, okay, yeah, that's annoying, but we can add that back in. There we go. Struct target star T. Target star T. Not sure why that's complaining, but okay. Oh. Close that one. Oh, probably because I've said struct, and it's not a struct, it's just target. Like that. Yeah. Okay. Oh, and I've got a squirty brace open. Whoops. So let's see if this builds. No it doesn't. Ooh. Okay, so I gotta go revisit command. So this is static. Cool. This. Okay, that should shut up that first error. The other two are caused by the fact that we're not using argc or argv on a project that is only buildable with Wera, because it's hard-coded to be Wera. SPI.h no such file or directory? Really? So in OpenCM3 here, under STM32, there's GPIO and SPI. Oh, which one was it that was using those headers? Because it gave a pretty good indication as to how to include them correctly. Oh, general is where. General platform. GPIO. Interesting. We'll come back to this, by the way, because this is where we need to do some fun stuff with the monitor command system, which is these Q packets. QR command is monitor, as it turns out, which passes off into this. Is there a thing in the native target? No. Oh, hi. There it is. There it is. That's how to do it. Build out on a Boolean expression. Fine, I'll just invert instead of using bool. Oh, sorry, instead of using tilde. Type as an unused variable. It's not wrong. See if that cleans that one up. Static used in inline function. Why is that an error? Why is that even a warning? Can I say static inline? Is that a thing? I didn't think that was a thing. I should get a compile error out of this, I'm certain. Oh, never mind, I can do static inline. Okay. I'm just going to comment out the ones I'm not using. Hey, there we go. Let's see how big the firmware is now. Ah, that's not bad actually. Only 99k. That's up by like 1 kilobyte for all of this. So we have the addition of the flash scan chain stuff. Yeah, I think I'm going to split this into 2 commits. So we're going to do add SRC target onboard flash. Not P. That's just straight up an add. Along with the make file change required. Created a new SPI attached onboard flash target. And then we have these 2 changes, the stuff to add the scan, and the header change, yeah. Created a new scan type for the onboard flash. So, okay, now we've got that all done and working. Well, at least theoretically working. I don't have the hardware here right now to test that. I'm going to switch up gears very slightly, and I'm going to start looking at how we need to pack an ELF file to go into this flash that we've just prepared the ability to write. So, I need some code off to one side that I can't show you, which uses GLF and liblf to be able to poke and prod ELF files, which is hilariously fun. We are now going to create a tools directory, and I'm going to use Meson for this because, well, I very much need to be able to go and find system libraries, and this is very much a pain in the ass to do for these system libraries with a makefile. Unfortunately, I have that experience. I'm not going to fight this. So, no, I don't want you to configure that. Project is going to be Blackmagic Probe tools. I'm going to be using C++ because, again, I just want something that's fast to write. I don't want to fight this. Default options, I'm going to use CPP stood C++ 17. Warning level of 3. An out-the-box build type of release mode with stripping. Version of these tools is going to start out at 0.0.1. And we're going to want to force use of Meson version at least 0.53 for various reasons. With a subproject directory called deps, because we are going to need to use substrate. And if I copy from data electronics MX keyboard deps. Is that not got a deps directory? SPI Flash programmer deps? There we go. We'll copy the wrap file. And then we'll grab substrate itself as a dependency. We don't need to set native true because this is not a cross build. We need other dependencies we're going to need gelf and libelf. So if I do gelf libelf, then yeah. So there's one of the two headers, and there's the other of the two headers. Okay. Question I now have is... is there a PKG build for this? Sorry, PKG config for this. libelf. There is. Now I'm going to need a very specific minimum version. What version have we got here at the moment? That's the next question, actually. This is 0.185. What's the version on Debian right now? That's the next question. I'm checking on a Debian machine that's to my left. Which, oh, right, it probably doesn't have it installed right now. dpkg algrep elf. 0.183. So let's go for probably version 0.180 flat as the minimum version. We then have the Flash tool SRCs, executable Flash tool. Ooh, actually, no, I want to call this BMP Flash prep, something like that. I'm trying to think of how to do this because we actually do have a main executable already called Blackmagic, which you can run to interact with this ecosystem. Only currently it's broken in my copy because some fun stuff, but so this would be Blackmagic Flash prep probably. Flash tool sources, dependencies, substrate, libelf. I am making a Meson build, yes. And that's it. That's everything needed, I think, to have a workable Flash tool. Indeed. Not depths, tools, there we go. So if I now touch, we're going to want at least flash prep.cxx. Yes, I'm cheating slightly by having another one up and using that. Yes, this is the binary to ELF conversion tool. I think I want to call the next file yeah, actually I'm probably going to call it the same as I did in the other thing. Firmware ELF. Firmware ELF. HXX. Oops. Makefile tools is having a bit of a time, which is fine. So we have int main taking parameters which we haven't yet got defined. We probably want to grab. So this is Meson build. And now if I copy in from here, Blackmagic Probe ELF, we'll use that as our source file to pack, just because it's got sections in it that are meaningful and so on, and it's a base file. I have used Meson for embedded projects, and in fact that's actually what I was ripping stuff from. SPI Flash Programmer uses Meson as its build system, as does the MX keyboard firmware. Oops, I sent that to the wrong screen. Supposed to send that one to that screen. There we go. I very much approve. Well, the really fun part is we've already got a building thing. With just that much. And this build system now doesn't really need to be touched, save for adding firmware elf.cxx into here. This is already allowing me to use substrate, this is already allowing me to use liblf. Good to go. So if we do... I'm trying to think how to structure this. So we've got our ELF file, if and def firmware ELF hxx, define this thing, and if should also add licensing into this. We still have 20 KB left, yeah. I can actually go and put Blinky firmware in there and try out some of this stuff. Probably. Well, that will be next stream I do on Blackmagic Probe. So we have substrate FD. And I'm trying to think. ELF is coming from Gelf, maybe? Oh yeah, display stuff is going to consume quite a bit of space quite quickly. That's, yeah. I wasn't going to tell them about that yet. So we've got an ELF file, inside of which we have a handle to the underlying file, and we have an ELF file, which I'm going to actually use some magic for, but we'll come back to that. Because I think I can use resource acquisition as initialization patterns here to help me a bit with the management of that pointer. So public ELFT and this is going to need to take a const char star const file name. We'll also want a way to initialize this thing. I should just call that init, because there are some things that have to happen exactly once in this for liblf to work correctly. So if we do elft init, if ELF version, alright, you also need to include the ELF headers here, which are these two. My editor's getting very confused right now because it knows about both a make file and a Meson build file, and it doesn't quite know which one to use here. So that's why that's being a bit weird. Let's see, we've got... Oh, I put those two in the wrong file. Whoops. There we go. ELF version, EV current, EV none, return false, return true. So these are things that come from elf.h, which is included by liblf.h. I think this might also be where that master ELF type is. Gosh, I really do sometimes absolutely detest the liblf headers and the way it's written. So user include liblf. It's way down. I have a lot of headers on this system because this is an Arch system, so I have headers for everything and anything that I could ever want. There it is. Oh, yeah, it's just a transparent structure. Excellent. That makes my life really easy here. Make that a transparent definition. We can make a pointer of that at any time we like, and that is correct. So, Substrate makes opening files really, really easy with FTT here, so I can just do an FTT on file saying I want to open RD only with no controlling TTY, and that's already the file open done. We also probably need to do some initialization on the ELF file member. But for that, I'm going to use a lambda because I need to make sure that FD is not a bad file descriptor when I try and pass it into ELF begin. Otherwise, ELF begin explodes. So we capture this. I'll put that at the end there. Capture this, like that, and then if fd dot valid, sorry, not fd dot valid, return null footer, otherwise return elf begin, file descriptor elf c read null footer. And this should now create our pointer to an ELF file and should just work in theory. Well, that exploded in a fun way. Part of the reason for it exploding is because using substrate FDT. I actually need to pull it into scope. Welcome back, Aki. Struct TLFT. I appreciate that. I might do that. Although, in this case, I already have code that uses liblf that I'm basing this off of, because I've actually done firmware repacking once before. But I might still use it, because, you know, it's nicer code than this. So we now need a validity call, and the validity call needs to do a couple of things, which is fun. Oh gosh. This is actually const. Also, yeah, how does the destructor work? The destructor needs to call ELF end. Which I think can take a bad ELF file in and not explode. I need to check what that does if you handed a null pointer. So, valid needs to do a few things. First is if not fd.valid or not ELF file, return false. Otherwise, we need to pull out the kind information. And if that is not ELF, 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 I think it is. File, Blackmagic ELF. Yeah, this is an executable, so we're looking for a KELF that is executable in 32-bit and some other fun bits. And this is another place where Substrate is going to come in super handy. It has nice console handling. So if we do console is stood error stood out stood error, and I include console and using Substrate console we can now do console.error file is not a valid ELF file. Type was %x string view. Oh wait, that's right. I'll pull out as hex into scope in just a moment. I need to pull string view into scope. And then we can do a using substrate as hex t. And I think the defaults for as hex are pretty sane for what we're doing. Yeah. Welcome, welcome, Amy. Or rather, welcome back. So for right now, I'm just going to elft emp elf is blackmagic.elf. If bmp elf.valid, if not valid, console.info error reading the bmp elf. I mean, I would like to do that in the better version of this. I just need something that works now. There is unfortunately a time limit, effectively, on this code being written. I need the code to work by the end of the month. So there is a time limit. Right. Let's see what happens now. It still explodes. Class template document deduction failed. Fun. This is in the apps substrate. Oh, right, it's using the system substrate. I can tell it not to with force fallback for substrate. And now it will use the substrate that's from clean cache, is it? Oh, wow. Meson configure clean cache. There we go. Bingo! So it's now using the one built into the project rather than the one from external. Also, it seems like I forgot to tell it not to build the tests. Oops. Yes, I did see. I'm finding that pretty awesome. Which is why I now have a catch 2 wrap there, which needs to become untracked. So... yeah. And I'm using substrate as a wrap here so that you don't need to do a submodule, sorry, a recursive clone here either. That's another big benefit, by the way, Eston. With Meson, if you're using wrap files like we are, which are these really tiny things, it eliminates the need for git submodule clones. Completely. And it's great. And yes, you can pin to particular versions, etc., using the version stuff here, but you don't have to, and you can do it as well in the wrap files, but you don't have to. So it will always, in this case, it will always pull the most recent substrate. And that's done. I unfortunately did screw up in one little place here, which is that I've completely forgotten to tell it to use the default of don't build the tests. Which I've forgotten how I do. If I go data, electronics, MX keyboard, substrate, not substrate, cat Meson build.
In a very special way.
Meson build. Oh, which project was it that... I I'm trying to remember how I tell Substrate not to build its tests using the default stuff. Now I was gonna go and find an example. Oh, Lib Audio. Probably. Yumakui could also work, yeah. Okay, fine, I'll go and look for Yumakui again. Not Yanka. Yumakui. Software. Oh, and that also has the extra warnings list. Ooh, goody goody. I should add that. Control Shift C or not that. There we go. Oops. Consoles are sometimes problematic. I'll come back to those. I'm guessing it's in the Dreamcuttle utilities. Ah, there it is. Default options. I don't actually want to make a static library of this though. So if I do Meson setup wipe, it will start over for me. Oops. Looks like I was right putting it at the end. Wrap redirect file name must be in the form fusa project bar.wrap. Is this upset at me again because... Yeah, it gets upset because it does this and then it gets unhappy. Unknown statement. Oh. Oops. There it goes. Much better. I only built 8 things that time rather than everything. So I can now actually probably go and find the right header file if I follow that. No, because the environment is still not configured properly. Wonderful. Substrate, console. There's hex. It doesn't know how to convert a kind to, sorry, a type to, Meson's wraps lethal bit? Huh, that's an interesting one. Yeah, it doesn't know how to convert ELF kind enum. It's an enum, so I think this probably needs to be uint32t. There we go. So we have to do some more identification stuff there, but at least this should just work. If I rebuild again. Bingo, it can read the ELF file. Perfect. So let's do the identification and then add what we've got. Also, before I do, I'm going to quickly open a window because I'm getting very, very hot. Which, yeah. Okay, we're back. I'm trying to remember what ELF get ident takes and how it works. ELF get ident. Okay, that gets us the identification information. If ELF ident len not equal to EIN ident, or not ELF ident, or ELF ident EI class. Oops. Keyboard malfunction. ELF class 32. Oh. I'm trying to remember what is in that identification section for this file. XXD to the rescue, I guess. So N for number. False. Oh, len. L for len. We want 128 octets. Does that actually show the decoded raw header? With all the bytes intact? Oh, okay. Oh yeah. Hey, what do you know? ELF header. Complete with the magic and everything. Oh, perfect. I'm trying to remember which header this is in. The identification data is really, really annoying to get to because it's split into like 3 different header parts. So there's Gulf, Elf, and libelf, all of which are actually the same library. It's just the header split. GELF. No worries. And we will come back to Gulf in a moment because that's the general ELF interface. ELF. H, there it is, there's the other part. So there's ident. That's where ELF class 32 is defined, along with EI class. We then have ELF ident. EI data is not equals. Oh, actually, this is. I can do this as a massive return statement. So this is going to be looking for the data byte 0, 1, 2, 3, 4, 5 here, which is little endian. Yeah, 2's complement little endian. That's what data is. Should be that. And then there's the version information, which should be the current ELF version. ELF ident OSABI, which is the next part. We want this to be system 5 for reasons. The ABI version needs to be 0. I defined, in my case, separately. Okie dokie, take care, Aki. Sleep well. You also want to check things like the machine type. Oh, it helps if I actually pass that by pointer. Oh, silly sausage, Aki. Sleep well. There we go. So okay, we've still got this working correctly, so it's correctly parsing its way through that identification data and matches all the requirements. Oh. Welcome, Elms Twitch. Thanks for the follow and welcome to the stream. So, we want to add, let's start with firmware ELF and Flash prep. Actually, let's also add the build system. begun writing a flash packing tool for the onboard, converting ELF files for the onboard flash chip. The next thing that we probably need to add into this, if we look in tools, depths, we now need to add substrates wrap. Added the dot wrap for substrate. We also need to do a git ignore, and this is going to be for catch 2 all versions, and package cache and catch 2 dot wrap. Oh, and substrate too. Because that one always gets recreated as needed. There we go. So I want to we've got basically an input name and an output name for a given file, so we need to kind of store the input file name, the output file name, well, handles, not names, sorry. I can pass a file descriptor in, so if we have full repack taking a FTT reference, I don't want to name it like tooth file. Output file. And this is also going to be const because it does not change the ELFT object. Let's see. FDT BMP bin is going to be blackmagic.bmp bin. We want to, if not, bmp bin dot valid. I'll add the missing options in a moment. Console error, failed to open output file. And this is a fatal error, so let's return 2. Otherwise... empty bin... console error, failed to successfully repack ELF file, which is also a fatal kind of error. Otherwise, console info repacking completed. I should also make all of these string views, jeez. Oh. One string view too far, there we go. Right. The options I'm missing here are R only, O no CTTY, and O preact. And it needs to take the normal mode, otherwise the file will be created with garbage permissions. Yeah, that should give me a standard non-executable output file. So... Gulf EHDR ELF header. Jeez. If we can't do a Gulf get EHDR on the ELF file into ELF header, or ELF header E-type is not equal to ET-exec. That is making sure that this is an executable file, which should be an executable. We also want to then check the type is ARM. Oh yeah, there's some fun stuff in here, isn't there? Yeah. We are after this one. ELF header, E version is not EV current, that would be a problem. And we want the I actually don't care about flags in this case, because we could be repacking any ARM ELF file, and I don't care. The vendors did. It's been assigned out to whoever started using it first, so they're basically sequentially given out. Somewhere in here should be, like, there's Risk 5 right near the end, because it's the most recent. AMD GPU is the next most recent that they issued out. They reserved an area. BPF then came after Risk 5 in this slot. In here somewhere should also be the pick stuff, which has a very entertaining hex CC, so that should be 204. 204. Yep, there you go. Microchip pick. You don't want to know how I know that and why. But yes, you can actually get the pick tools to put ELF files out. The code I'm using as the basis for this is actually based around that. Heavily. Oh, I know you know, the rest of the stream doesn't though. Let's see, we then need to get the number of physical headers, Well, we might be now. 8 viewers. Oh. So this is a size T physical header count. Oh. This is still not going to tell me how these functions work. Golf get physical headers. Where's the physical headers stuff gone? It's going to be easier just to run a find like that, isn't it? Oh, that's not a Gelf function. That's why I can't find it there. That's a liblf function. Gives a number. It doesn't tell you what that return value means, though. That's annoying. Anyway, the next thing we need to do is we need to build a map of the physical sections that the file has. We'll call it a segment map for the purpose. So this needs to map physical addresses to logical addresses to physical addresses, and ew, yeah, it's gonna be fun. Oops. Just a semicolon. That's where we define it down here. So that'll be an empty segment map. We then have to... we could. I don't think that's actually very useful here. I don't think that these are big enough files to merit that complexity. I'm not sure you're going to get very much out of RLE in this case. This is actually const auto I for substrate index sequence T physical header count. Oh. I should probably go and get myself a drink. Substrate, index sequence, I think it is. Yeah, index sequence, perfect. So what this is allowing me to do is, instead of having to manually write out the for loop and make sure I get it correctly bounded, etc., I get it all generated for me for free. Because yes, I was crazy enough to go and make a type that gets rid of normal for loops completely. Oh, this isn't physical header count, this is program header count. There we go. I'll get there someday. So we do a gulf get program header from the ELF file, that index, prog header, and if that is a bad result or the program header p file size is insane, oh nice. Yeah, I need to sort out affiliation. Is it capital S? No, those are the section headers. The program headers are L. Okay. You can? That didn't used to be the case. Hmm. Okay. I'll figure that one out. Because that would be quite fun to have. Program header, file size. So if this is something insane, like if this is equals to that, and likewise if the program header offset is insane, then we failed to read a good program header. Let's see. So we've got all the program headers read. We want to only include the ones which are loaded. And which are non-zero in length. And if we've got a reasonable looking header, or rather, reasonable looking section, add it to the segment map. It would be really nice now if, well, okay, I probably need to include map, and then that will start working. Yeah. Okay. So we do it in place at prog header.p draw the program header. This is segments. I forgot to give it an ampersand on the front of this. Okay, found two segments to repack. Perfect. Didn't actually do the repacking yet, but that's a good start. Yeah, let's do some version control. Built out logic enough to trial run the repacker. So there are section headers as well. So if I look at those, there are these two things. There's one that's loaded at address 0, and the other which is at address whatever that is. It's very high up in probably RAM. Now, yeah, that would make sense, because if it's RW, now there's also the section headers, the S headers, and we are looking for the yeah, I was right, that is RAM. I'm trying to remember why I'm doing what I am in the section headers on the other thing that I wrote. It's been a very long time since I last did anything with this though, so, See, text here starts at this address, well, at this address. We've got an offset, we've got a size, and if you actually take the size and you add it to that address, you get to this location. These are 0-byte sections, and then there's the ARM EXID stuff, which is at the very end of that. Before we then get the data and BSS sections. I have a funny feeling that what I'm doing in my code base that I'm copying from a bit here is that I'm looking for what are basically these prog bits ones, but I'm not doing it by this type, I'm doing it by it being a non-zero size and the addresses being available inside the map I've just gone and grabbed from the physical headers, the P headers, sorry, the program headers, not physical. And that gets rid of things like the symbol tables and debug information, and it just gets you the raw information and exactly where it needs to be written into the target device for it to all work. Whereas the program headers give you offsets into the file for where to find that data. It also gives you the virtual addresses that the data gets loaded at. And it gets you some size information. So between these two, when you kind of mash them together and you fix everything up, you get a overall look as to how the program is actually laid out for repacking. I think that's what this is doing and how it works. So I've got the number of usable program headers. We then have size T, this is section headers. Yep. Sect header count, ELF get S HDR num sect header count. Let's see, we've got the section headers themselves. There's also ELF SCNs. Well, actually, this is const auto section ELF get SCN. I don't recall what an SCN actually is or does in this case, but I know I have to do that to then do a GLF get SHDR using the section information we just grabbed and sect header. So this is taking that section address that we've got here and looking it up in the physical header map that we've already pulled and mapped, created the map for. And if the segment is non-existent, we continue. What this does automatically is all of these zero mapped things that are not in the real file because the physical addresses of things start with hex 08 and a whole pile of zeros, none of these will look up correctly except for these ones, and of those ones BSS is not a physical header location, it is above the virtual address. Data is the virtual address, so we'll pull data. The ARM EIDX data would have been pulled if this was a valid header. Yeah, we have to pull some very interesting stunts to get at what we need here. And then all of this stuff will get dropped like hotcakes because it's empty, leaving us with .text. So we get .text and .data this way. It's a very complicated way to do it, but it's a way that always works without hard coding. So we can now grab a const auto reference, prog header is segment second. I could do the get string section thing. Do I need to do that? No, I don't need to do that. But what we now have is we actually have the exact data to do stuff with. So we can actually do a seek to the right location in the file and start reading data. Now I'm trying to think. So build 4K header at the for the start of Flash. What I want to first try and do is take the sections, read them out 4K at a time, or up to 4K at a time, and then write them to the output file and add the extra bytes at the end as hexff needed to be able to... yeah, the FAT. Flash allocation table. So we've got our own FD, which we can do a seek. Oh, what's the name of the seek operation that we can do? Tail goes to the end, head goes to the front. I could have sworn we put some seek helpers in. Oh yeah, seek roll. Is there a seek abs? No, there isn't a seek abs. Oh, that probably actually makes sense, because I can do that with this function directly. So this takes the offset to seek 2, which GELF, bleh. Where's the program header stuff gone? Oh, right. GLF goes and says everything's a 64-bit binary now, for simplicity's sake. So that can actually be greater than or equals to, as can that, and that's fine. So it is... bleh. One of these headers has the thing I need. There's the EHCRs. Oh, this is underneath this massive long list. There we go. SHDR... section file offset. Yeah, is that really a thing? No, that's not the real offset in the file. That's the offset in... ooh, fun. Oh, Aki's gone and talked to me into going and getting some PC Byte stuff, which... P offset, there we go, that was what I was thinking of. it does look really good, to be fair. The PC Byte stuff seems like it's really just good. Yeah, exactly. That's the exact kind of thing I want it for, because I keep having that happen to me. I'm like, I've not got enough hands! So... So, we've done a seek to the right offset location. We can then read the... I need to grow a few more pairs of hands. Sure. I could do this as a stud array allocated on the stack, but I think I want a page pre-allocated out here. We'll call this the segment buffer. Oh, no, I do want this on stack, actually. I just don't want it in the loop. Yeah, I just need to grow a few more pairs of hands. Yeah. Because if we want to be able to repack multiple files in parallel, I'll have instantly shot myself in the foot. Plus, there's 2 megabytes of stack, so I can use the stack. I could have marked it as a, nah, that's fine for the stack. I could have marked it as a thread local. That would have worked. And then it'll automatically have an allocation created when we spawn a new thread, but I don't really feel like going and finding how I do thread locals right at this moment, because I don't tend to use them. It's all good. I'm just having that moment of, oh yeah, I actually need to check this against the amount of data left to read for the section. So there's size T, read count. There's size T offset. And size T amount, probably. I think that's probably what we want. So we've got 4... for offset, 0 offset less than frog header p file sz, which is the file size version. Yep. We don't care about the memory version of things because we're dealing with what's in the file. So offset plus equals segment buffer dot size. Gosh, Dubmood does such good stuff. Yes, I know who it is without looking at the... I can't currently see what my music player is doing. I just know that this is a Dubmood song. So the amount we want to read, that's what we've got here, is going to be std min of segment buffer size and prog header dot p file sz minus offset, which is whichever is smaller wins. So what this will do is it will give us the ability to read up to the section size bytes at a time, but based on whatever's left to read versus our 4K buffer. And we can then stuff that in as amount there, and then we have read count as the result. And I think this returns the raw number of bytes read. No, I don't remember how that works actually. I need to check that. Oh, right. Doesn't take a ref on the front, it's just as is. And I forgot to terminate that assignment. Cool. Comparison of different things. Long unsigned int versus that. So I actually need to do a conversion to offset t. This will be round brackets because I'm doing a signed unsigned conversion. Okay, it does return a bool. So if this fails, this is because read itself actually failed. Failed to read. Oh right, I don't actually need to care about how much got read. I just want to care about how much. About requesting the right amount of data and having FD-read deal with it for me. Failed to read segment data. Otherwise, we've read the segment data and we then want to output file write segment buffer data amount, and if that fails, console write. Oh right, no, I want to write segment buffer, and I'm going to do a polyfill here. Failed to write segment data to output file. Source ELF file. So what we want to do is we want for const auto ref j in substrate index sequence t amount segment buffer dot size. So what this does, in index sequence actually works kind of like a Python range. So you can either give it an end, a total number of things to iterate, a total number to iterate over, or you can give it a begin end, and it will do the iteration between those 2 points, which if they're equal to each other is a null iteration. Which means that we can go from the end of where the read wrote to the end of segment buffer, and that will always do the right thing. And I can now just do that. And now we've just done the padding. It's a very sweet for loop. Oops, that was the wrong thing to run. Some SVs there. That's error, not right. There we go. So that repacked the file, and if we now look at that in a hex editor, dhex is probably going to be the easiest thing to use here. Interesting. That's an empty file. That's why. Why is that an empty file? Not printf. Console. Debug. Looking for section I in segment map. Section has address as hex t. Yeah, good, that's in scope. Header sh address. Yeah, I could do that. This is still going to be useful to be able to have debug info in. So, I'm just going to quickly put some debug stuff in, just so we can trace it for when a user's machine's deciding to have a bad day. Because you can turn the debug stuff on and off in Substrate, if I recall correctly. So, found section in segment map attempting to seek to it. We also should probably put out the number of segment headers we get. Is this the whole physical address versus virtual address thing? This might be a physical virtual address problem. So if we look at the physical addresses. These addresses. Data is at its virtual address. We should be looking at the virtual addresses in the map, not the physicals. So segment map. This is the V address that we want. Found a section attempting to seek to it. That's a good sign. And the other one is 0800200. Why is text offset like that? Oh. This program header shouldn't define itself to start there then. It's technically an invalid header. Oh, that's annoying. It works, but like that's gonna suck. Yep. But the firmware is the only bit in here, not the bootloader. So technically speaking, because the text section starts at this offset and there is nothing at the offset given in the program headers, the program headers should actually be for the firmware's start. Strictly speaking. As I say, it works, but this is going to be a pain to rectify because... yeah. But that size matches the one down here if we add up the EIDX stuff as well into there. So... because this does not know about that kind of offsetting. So that virtual address is never going to match. This is problematic. We'll have to then look and see. The problem I've got is that if I add the physical address, yeah. Well, so the problem I've got is if I add the physical header address to the physical header size, even that is not going to match the start of the section header, so the section's not strictly speaking considered to be inside the physical segment, because the physical segment's not big enough. I'm looking at the fact that this address blows clean past the end when added to the when adding its size to its address. It blows clean past the end of the file size of the mem size thing, I think. Oh no, it doesn't. Okay, we can do this. This is going to be a little punitive to do, but I'm going to end up just having to write a mini loop that gets us the... yeah. No, I can rely on the header. I'm just going to have to write an extra function to do this, because I'm going to need a special thing that will take the map and the section header and basically for loop its way through the map, looking for a program header that fully contains the section. So if we do segment is map segment map sect header. If it's the end, then continue, and then kind of, yeah. I can't do it with find though, so it's going to be horribly inefficient, because find actually is surprisingly efficient. So we do, I'll call this auto for now, map segment map t map segment map, and then const g elf shdr sect header for const auto this is going to be for prog header in segment map. I think that's right. Oh, no, I have to do program address and program header in that. If sect header dot sh addra prog addra less than or equals to that, return end. If I'm gonna need two bounds. I'm gonna need const auto prog hdr end is prog header dot p b addra plus prog header dot p while sz, I think it was. I think it actually might be the mem size, not the file size. So if we do that to get the end of the header, so this is prog HDR begin. If sect header sh addr less than or equals to prog HDR end, sect header.sh addr greater than or equals to prog HDR begin. I can get rid of this outer statement actually. This will be sh symbol information. Where's the section header gone again? Oh, is it dynamic entries? Rel Sims. Ah, there it is. Section header was just a bit further up. sh addr plus sect header dot sh. Hey, the Paragoso, welcome. We are working on Blackmagic Probe firmware and a tool for repackaging ELF files to go into Flash that will be present on the Blackmagic Probe, so that we can do new functionality to allow you to click a button, and if you've got something in the Flash and a suitable target, it will find the target, connect to the right chip on the or the right part of the target, and reprogram the flash of that part of the target. We're currently doing the repackaging tool. So we got section header end is the section header address plus the section header size. There we go. So if the begin, and then if end is less than or equal to the end of the program header area. So that's if the section is completely contained. Yes. Then return. Oh. I actually need the iterator. I need to do this the dumb way. So we've got begin is segment map begin segment map end Okay. Yeah, it's not nearly as nice, but we now have the... I'm actually inclined to get rid of program header begin there entirely. I'm just going to make that an underscore, and we can mark it unused if we have to. I keep managing to misspell segment. Segment. Where have I misspelled segment again? Huh, there. Hey, there it goes. It's picked all of the proper stuff up now. So if we look at Blackmagic, BMP bin, it thinks it's got like missing section headers and stuff, but that's fine. If I now look at dhex, probably. I need to go right to the end, then I'm gonna have to zip back forward. Well, hey, there's some padding for you. So the padding engine worked perfectly. Yeah, there's padding in between these sections. That couldn't have worked better even if I tried. I don't know why we're getting ELF headers at the start though, that is a little bit weird. That's address zeroed, those are address zeroed, they all get dropped, that's correct. Section has addressed that. Found in segment map, attempting to seek to it. It's padding to full 4K blocks, yes. We can probably get away with doing to 256 byte blocks, but I think this way's better because then we can actually erase just subsections if we need to. We don't have to erase weird off-sized amounts and have GDB freak out. So I think this is fine. Nah, it's not too bad actually. Because we're going to be storing the offsets to the start of each of these, it's reasonably trivial. Also, I can do the fun thing of seeking back in the file and rewriting a section of the file. Because I'm actually going to seek forward 4K. Oh, I see. Because I could actually do a 4K 0 page at the start of the file that we can then come back to using seek, which is kind of cool. So those segment headers all look correct, but I'm not sure that the seek addresses are all correct right now. So if we go looking at the program header stuff again, Next line. Segment file offset versus the section. Section file offset. Yeah, this shouldn't be using the program header. This should be using the section. I'm not even sure I have to pull out the program header. Let's look at the section header. SH offset. And if we then do section size in bytes, yeah, that should probably be the one. Now it doesn't think it's an ELF file. Yeah, okay, that makes more sense. Uh, 2050, that looks like that is the start of the stack, and then 8001, sorry, 0012205, that looks like the address of the reset vector. That's a good sign. Hmm? Surprise! I did announce it on Betty, but I understand if you weren't looking there. Yeah, all the program's strings appear to be here, Eston. We don't need the string section. The string section is strictly speaking only for translating the names of, the string section is strictly speaking only for translating the names of ELF sections, that kind of thing. It is not used for the actual content of the ELF, the raw binary. So, this all looks good. That leaves us needing to do the, what you called the FAT. Yeah, we have XML in here. It's great. So, full 4K header for the start of Flash. Ooh, awesome. I know what you're talking about. Nobody else here will. Yeah, your compression idea should gain us a big pile of memory. It's great. Uh, 4096, seek set. Error, not info. Failed to create Flash header hole. She's playing Minecraft. How to create a Flash header hole. This is where the hard work comes in, though, because trying to... I have to come back and write the header. So I was planning to reserve 4K at the start of the file. And that didn't work. Also, it helps I have a ton of code already written for this kind of thing, so, like, I've not been having to go and dive too far into the Gelf interface. Let's do a quick bit of version control. The main section repacking logic. Oh. There is actually a find missing function, Hexgen. I'll show you how it works later. Right. Header at the start of Flash. So the header that we need to put at the start of Flash, let's struct Flash header T is final, and let's start putting the members we need in. We're gonna need we are going to need a checksum of some sort, probably a CRC32. Because that should fail for the header being all high values, so we know it's invalid if that's the case. There's a quick way to be able to check for the invalid header. Then also that means I want to copy in which project did I do the CRC32 stuff in? That would be Apong. Then after that we need a section count. So how many sections follow? We're going to then need a table, essentially, of the actual section offsets and lengths. Yeah. So let's have flash header T, flash header. I think I'm also going to add some magic header bytes, because I can. The SPI Flash, that's what that will stand for. Because then it makes it really easy for us to be able to know what's in there. Need that to be initialized to a bad value, and then those can be default initialized. Oh yeah, we'll also need target information. Yeah. That can come after the CRC, but before the sections. Let's get this bit working first. So we've got a flash header. Yeah. Yeah. I really need to get that drink. 1 second while I go and put the kettle on. So we have section header, we locate the section, make sure it's a valid one for thing. So at this point we can do flash header section count is incremented. Oh my goodness, there we go. In actual fact, ooh, yes, I don't have to expose that because that can be calculated at the end of adding all the sections to the thing. And the flash section... offset is going to be... offset is going to be... output file.tell. Which tells me where I am in the output file. And then the length. So these also both need to be pre-initialized to 0. And then the length can be incremented every time we go through this loop. Do an in-place back. Flash section. Actually, it would be just as sufficient here to do a pushback. One moment, my kettle is boiling. And back. Okay, so I was actually having a quick think about this. I don't actually need the CRC32 inside this exactly. What I actually need to do is I need to have a function that copies the header to that output buffer, that array, to be written to the file. Yes, well... it's a nice Earl Grey. Yes, very British of me, I know. I'm actually inclined as well to split this out into two more files, one called Flash .cxx and one called Flash.hxx. We'll come back to that idea just in a moment. We have the segment buffer there. Yeah, so we can do flash header to segment. To page. Nice. Ah. Today I learned. Interesting. But it's actually from the orange family, if I recall correctly, isn't it? Yep. Bergamot oil. Which is, very nice and citrusy. Else if output file write fails for segment buffer, console error, failed to write the flash header to the start of the output file. Otherwise, we are good. Let's add flash CXX and flash HXX. Allows us to maneuver these out into here. I'm also going to need array. Tentative definition has type that is never completed. Eh? Huh. Anyway, we now need to pull that header in here. Oh, yay. actually going to pop that over there, along with this header. That'll make my life a little bit easier. I'm sorry, but I'm not sorry. Well, yeah, welcome to Halt and Catch Fire server, where everything is many, many, many stacks of a resource, and nothing is simple. I mean, Eston, I don't know that you can be given fault in this case, but sure, thank you. Give it a default constructor. Does that make it happy? No, it doesn't. There's probably a few things that are annoying about that bolt's design, seeing as it was designed by someone who doesn't normally design piston bolts. I'm gonna have to show people what I'm talking about, aren't I? I would suggest you please do the alternation, otherwise you're gonna run out of sea lanterns real fast. Plus, it's also a waste because you'll never see the lanterns that are underneath the, We do? Oh, I would still say do the alternation. Stone's cheap. Or cheaper. Okay. Fine. Anyway, right, so we've got a flash T, header T, created an initializer, that has got a semicolon on it. Semicolon on it, even. Yeah, this is a very weird Clang Tidy error. We've got some private members, trying to get that to move over was being a pain. Right, so we have... Page buffer starts out by having mem copy. That's in the strings header, isn't it? Yeah, there we go. So this is destination, source, length, So this is going to be do. I should probably try it at some point. No, I haven't yet used Wavetron. So we got the CRC32. So that's bytes 4 to 7. And then following that, we then have the section count. Good to know, actually. ASCII art for the win. So this is then going to be oh, really? There we go. Because I won't remember that for too long myself, so I might as well write it down while I remember it. Otherwise everybody's gonna swear at me a lot. Variable has incomplete type void? It's not a variable. I'm going to pull that out into here. Well, that's not a... Oh, I know why that's complaining. I told ClangTidy that this was a C-only codebase. Oops. That was true until tonight. ClangTidy is not really smart enough to know that there are two projects in here in one go and automatically switch between configurations. It can be configured to be smarter if you do some runnery stuff at the base of the Meson project and everything uses Meson, but that's the Flash magic. So we start with the CRC32 being that, and we can then set page buffer data +4 to value FFU 4 bytes. We then want to uint32t section count is sections.size, which yes, I'm actually going to use an actual assignment for that because otherwise I have to do a type conversion shenanigans, which we can then copy that into page buffer data. Actually, rather than doing that, let's do std fill page buffer begin, page buffer end, FFU. That sets all the memory in that buffer to all high. Then we put the things we actually care about in, and that saves us some work. Make sure that that is the size we expect it to be. Okay. Yeah, ClangTidy is really upset at me right now, but that's fine. Because the code actually compiles fine. Ooh. Well, except for the fact I didn't yet add to the Meson build file. Those two. There we go. I'll fix the CRC32 code in a magic moment. Magic is no longer the name of that thing. It is Flash Magic. Perfect. So we've got the section count, and then we can then do so the offset we want to have at the start is 12. For section in sections, stored mem copy section to page buffer data plus offset. What does this need in order to compile? It needs includes c stored int and array. And that actually looks like about it. Oh, size t has not been defined. Okay, so stood def as well. Yep, stood def. So we've got CLC32 and some amount of data. Oh, that's literally perfect. And the result can then just be copied into page buffer.data plus 4. Ooh, fun, fun. Well, I've just completed the logic for converting our header to an actual page. And we can actually do... let's convert this to returning a bool. If offset the kind where I'm tired and I held the key down a little more than I should have. So if offset plus size of section greater than page buffer size, return false. Oh, I know. I'm having fun. I'm weird. Well, kind of. I still managed to, Very funny, Hexchen. I'm intrigued as to how I've managed to balk that. That's 4 bytes copy to the start. Section count. Oh. The section count was overwriting the other bit. Yes. There we go. That's why it looked weird. Yeah. There we go, there's some headers on the front. Oh, one moment, I have to close my window. Those who currently know my situation know why, and I know why I'm annoyed. Anyway. So that's our CRC32. Add P Nissan build. Edit that. It's nice, isn't it? Created the flash header and its flattening logic so it gets written to the front of our words. Fact. Binary. That'll do nicely. Cool. And I can never ever commit those two that I've left behind. I will always forever have !2 on my working copy. Fun is the reason why I can never commit one of those two in particular. And Eston should know the reason for that, actually. So, I'm going to switch back to firmware real quick before we finish up. And the reason is that we actually never initialized the SPI bus. We've used the SPI bus in the firmware without ever actually initializing it, which we should fix. Now, I think the best place to do that fixing is probably in... is probably in the native platform. Yeah, there we go. There's the hardware version pins, which we're actually now using for other things. Yeah. Yeah, we'll figure that one out once it works, I think. So the thing I'm looking at and trying to figure out is these pins here were the hardware versioning pins. We've got 2 chip selects and a special signal for a display present now in their place. Sorry, no, actually it's the QRSWO. Yeah. I think this will still read the version as being the highest version. Mm-hmm. Sure. And at least this isn't too hard to change to make that happen. To be fair. Right, so platform init. Platform init needs me to go poking... GPIOs. This probably is about in here somewhere. We can do a else if platform hardware version is greater than yep. Greater than 3, right? Looking at the hardware version detect logic idea. If it's greater than 3, then we want to do the thing. So we do GPIO set mode. And this is... Oh! What I'm actually inclined to do here, because we're constantly calling this platform hardware version, is pull it out as a variable that's just constant. Because it's gonna get old fast otherwise. This is a const int hardware version is platform hardware version. There we go. Before I commit, before I write the next bit, I'm going to commit that change. Let me do that in a place where you can see it. Okay, so GPIO set mode. How does this other thing do it again? This is to do SPI 1. Which is on port A. Yep, okay, that makes sense. No, this is for configuring the GPIOs for the SPI port to the proper directions. I was just gonna say port B there. Oh! Yeah. If hardware version greater than 3, then we want to set this to GPIO mode output 50 megahertz. Yeah, I'm happy to hard code this for right now. This is GPIO config output push pull, and then the GPIOs to use. Oh. Yeah. Oh, cool. The GPIOs are. That was for 4, 5, that's clock, and 7 mossy Chelsea is on 15. Clock is 13. And clicking on the wrong Chrome window. The other thing I need to make sure I set at that point is the chip selects too, which need to be port B5 and port B5 and 6. And then we've got GPIO set mode. Yeah, I'll do the clock setup in a moment. So this is input. GPIO input float. And this is GPIO 14. CPO. Right. Yeah, so that's now got the two chip selects, the clock and copy as outputs, and CPO as an input. We can now define the clocks required. Well, port B is already up. Yeah, they're normal GPIO. That enables the clocks for the SPI bus that we want to use. Yeah, that should do the trick, right? Because I'm doing the... I'm doing the initialization of the damn thing inside onboard flash here, which is probably naughty of me. I should probably not do that. Where's it gone? There's... here. This should probably be pulled out into the platform. I don't imagine us having to do much reconfiguration of that. It's pretty set and forget. I think that actually does it. That now has the reset for the SPI peripheral, the initialization. I need to double check. Oh, right. I need to double check that we are doing the right thing with regards to bus polarities. um... See, SPI operations, great. Zero, 0, and 1, 1 are supported. Yeah, pistons and repeaters if you've... Oh, actually, we tend to do the walls next, so that it's a sealed bolt, and then sealing, and then pistons and repeaters. Because you probably haven't put all the glass in yet. So I'd do glass next. So, Plug to 0 when idle is unclear what that actually means. I'm thinking because that's 0 and 0, this is correct. That's mode 0. Am I about right, Eston? I'd rather not have to go through the whole data sheet, that's why I'm asking. I'm gonna guess that's a quiet yes, I'm right. I think that does it. Okay, well, it's been 5 hours. We've got a lot done, and I really mean a lot done. We have a whole target written. We have a tool for packing binaries, although it is missing certain fields. Next time I work on this, yeah, quite a massive step forward. The next time I work on this, I will plan to work on getting a Blinky built for the target processor that this is all in aid of, and having Blackmagic Probe do an automatic button-based connect to the target, check what it is in it and all of that fun stuff, and then once we know what the target is, hit it with that Blinky in the format that we've just defined it to be in, using the repacker tool, and see if we can actually program a target from that repack data, but having that repack data embedded inside the firmware for Blackmagic Probe, because it should fit quite nicely. For a Blinky, we're talking maybe I don't know. Something like that, yeah. I'm thinking for a Blinky, we're looking at probably 8 to 12 kilobytes. Depending on how tiny I manage to make blinking LEDs. And how many sections it uses. If it uses exactly one section, that will be 8K. If I manage to keep that section under 4K in size. And if I use absolutely no globals. Which I shouldn't need to use any globals, so. My point is it should be really quite tiny. Yeah, 4K, so I should be able to do it in 8 because we've got the 4K header on the front. Yeah, fancy blink, cool. So yeah, the next time around, I will get a fancy blink working on the target using my normal Blackmagic Probe, and then we'll take that binary, we'll repack it, and put it in the firmware for the moment, because we don't have a flash chip present, so we can't yet use the flash target, and have Blackmagic Probe take a button input and run the state machine required to actually connect to the target, enumerate all of the contents of the SWD bus, and push that Blinky firmware onto the target. That will be the plan. However, that is not what I'm going to be working on tomorrow. Tomorrow, I am either going to work on the keyboard and getting the profiles system written and working, or possibly on SPI Flash Programmer, getting the verification side of it working. However, I think what I'm going to do is I'm going to work on the keyboard, because I really want to get some progress on that to fix some of the bugs I keep hitting. Like, you've seen a couple of times on this stream even, I had keys getting stuck every so often. Oh, perfect. Hi, Omni. I am just finishing up. I'm sorry. But we did get a good amount done, so yeah, repacking binaries and generally making a fun time mess. So yeah, that'll be interesting to see if this is all correct, etc. And like, this is a humongous binary. This is, for firmware, this is, you know, most of 100 kilobytes, which for firmware is just enormous. And you can kind of see part of why. Yeah, huge. But yeah, so we got the repacking tool written and working, although it needs a nicer interface. Like, it needs to be able to take the command line needs to take what what file you want to repack. So I should be able to do Blackmagic ELF to input file of Blackmagic ELF, output file of Blackmagic dot BMP bin, and of course it currently ignores its command line, so that actually didn't do anything different. But that should have taken that as the input and the output file. And likewise, I need to be able to give it a version argument and a help argument so you can see how to use it. That'll also be for a future stream. In my opinion, that is not part of making it pretty, that's part of making it work. but it's specifically because otherwise you're basically having to tell the end user, well, you've got to name your file exactly this and put it in this directory and run this tool and then move stuff out the way, and that's just... no. That's not what you ship to a user. They will forget. They will go, how the hell do I use your tool? -H doesn't work, -V doesn't work. So I want to add some very simple command line parsing for that. It probably won't take very long, maybe 4 hours, so yeah. But anyway, that will be for a future stream. As I say, tomorrow I'm planning to work on the keyboard, I think. I've just made my mind up. I'm working on the keyboard. Because I really want to do the profiles stuff and get the FN key doing a thing and deal with callbacks and that kind of fun stuff. And I'm going to hit you with another fun problem with the amount of space on the board, or not, as the case may be. I might have underestimated the amount of EEPROM required for what I want to do. So we're going to have to get creative. That said, thank you all for watching, and I will see you tomorrow at my normal time, normal place, for a fun programming stream. Another programming stream, I know. I want to do actual hardware dev again, but I need to get a couple of projects out of the way. So, Jana!